The Gabriel synthesis is a way to use an SN2 reaction to make an amine. So you would always start out with an alkyl halide, and it should be either primary or secondary. A tertiary alkyl halide would be too crowded. So if this carbon that has the leaving group on it was bonded to 3 other carbons, that would be too crowded. That would make it tertiary and the reaction wouldn't work. But so long as it's only bonded to 1 or 2 other carbons, this reaction will work. You can do this beautiful Gabriel synthesis. And essentially what you're doing is replacing the halogen, chlorine, bromine, or iodine, on an alkyl halide with a nitrogen. And so you're creating an amine. Now the specific way that it does that is with these particular reactants. You always have this thing called phthalamide. Now we'll talk about what's happening here. You also always treat that at first with potassium hydroxide. And then you always treat it with an alkyl halide, with whatever R group that you want to add. And in the third step, you always add hydronium or this other molecule called hydrazine. We'll walk through these one at a time. But the overall result is that when you do this reaction, the nitrogen in phthalamide ends up replacing the leaving group on the alkyl halide. And so you create an amine from an alkyl halide. Okay, well, phthalamide is what you always start with, and there are a lot of similarities between this reaction and the malonic ester synthesis, or the acetoacetic ester synthesis. Because if you look at phthalamide, and you can see what crystals of it look like here, if you look at the structure of phthalamide, you'll see that you have carbonyls. And now, after the last chapter, the previous chapter, on alpha carbon chemistry, whenever you see a carbonyl, you don't just want to notice the carbonyl, you also want to look at the alpha position. And if it has hydrogens on it, you want to see those hydrogens as acidic. In the first step of this Gabriel synthesis, you'll always treat this with some sort of a base. And the type of the base doesn't really matter. Here, a common one you'd use would be hydroxide, so something like potassium hydroxide. You'll notice that's always the first step in these reactions. You start with phthalamide every single time. You treat it with a base like potassium hydroxide. And what that base is doing is stealing off this alpha hydrogen. The base can steal that alpha hydrogen, the electrons would snap back onto the nitrogen, because the lone pair with a negative charge that forms on the nitrogen when that hydrogen is taken away, that lone pair is allylic not just to 1, but to 2 pi bonds. Now that has a negative charge, but that can exist in a p orbital that is parallel with the p orbitals on these atoms. And so it can spread out through all of those parallel p orbitals over all 5 of those atoms and stabilize itself. And we saw this similar position in the malonic ester synthesis. Compare this structure, pause the video, go look at a picture of diethylmalonate. Compare it. Notice that this is the alpha position, and so it's the acidic position, just like in that reaction. And just like in that reaction, we used that acidic position to take the hydrogen off and turn the alpha position into a nucleophile that can then do an SN2 reaction. Well, that's the same thing we're going to do here. It's just our nucleophile here is a carbon, is a nitrogen, not the alpha carbon that we had on diethylmalonate. So we can take this nitrogen nucleophile and treat it with the thing we have in our second step, the alkyl halide. So if you scroll back up here, you have phthalamide, you rip the hydrogen off with a base, that turns this nitrogen into a nucleophile. Now you can do an SN2 reaction with an alkyl halide. So if you have some carbon chain, just make sure it's primary or secondary, but not tertiary, and a leaving group, a halogen, chlorine, bromine, or iodine on there, then the nitrogen nucleophile can attack the carbon and kick the leaving group off. This is a classic SN2 reaction. Nucleophilic attack and loss of a leaving group. And what we'll have after that step, is the nitrogen will be attached to the R group and somewhere floating around, living its best life, will be the halogen. But we're not interested in the story of the halogen, we're interested in the story of this carbon compound. Well, we've formed a bond between the nitrogen and the carbon, but we still have this clunky, awkward Thalamide molecule attached. So how can we release what we want? How can we release the carbon chain bonded to the nitrogen? And then you see the amide. The nitrogen is attached to this molecule as an amide. An amine bonded to a carbonyl. And you can hydrolyze amides. And you'll remember this from a previous test. You drew the mechanism for the hydrolysis of an amide, the acid-catalyzed hydrolysis of an amide. Really, it's a nucleophilic acyl substitution reaction. All you need is H3O+. At first, it protonates the oxygen, and then water can attack this carbonyl, and the water ultimately displaces the nitrogen. So what you end up with is, first, an OH where the nitrogen was on both of those carbonyls, and then two H's on the nitrogen leaving group. Ultimately, it's a nucleophilic acyl substitution where this is the leaving group and this is the nucleophile. It comes in and ultimately after 2 proton transfers turns into an OH. And after 2 proton transfers, our amine gets those 2 H's, and so our nitrogen gets the 2 H's and becomes an amine. Now this is a byproduct, a waste product. But what we've really formed that's valuable is this amine. So overall, this is very, very similar to the malonic ester synthesis. You have this molecule, a special molecule, with a really acidic hydrogen on an alpha atom. The unique thing here is the alpha atom is a nitrogen rather than a carbon. You rip the hydrogen off with a base. It turns the nitrogen, the alpha atom here, into a nucleophile. Then it swoops in and does an SN2 reaction, kicks the leaving group off, and you have a new bond between the carbon and the nitrogen. But the nitrogen is still stuck, calcified onto this phthalamide molecule, and so you have to scrape it apart. And you do that by doing an acid-catalyzed hydrolysis. Now, you might remember that that is kind of a slow step. After all, that's why your proteins are amides. Amides are relatively stable. They're one of the least reactive carboxylic acid derivatives. And that's why our proteins hold together in all of the very violent reactions that we do every day, like breathe and sit. In terms of molecules, those are very violent things. Nonetheless, our proteins don't rip apart, and that is a testament to how stable that is. So even in the presence of acid, although this reaction will happen, it will often be slow, and you'll have to heat it up a little bit. So chemists have developed other nucleophiles that can attack and release your amine, and one of them is hydrazine. So hydrazine is like 2 ammonia molecules bonded to each other. So 2 NH2s bonded to each other. And ultimately, you pretty much get the same thing happening. It's just instead of the OHs, you have the nitrogens of hydrazine, which are bonded to each other. And so you still do, the mechanism is largely the same. This is your nucleophile. It comes in and replaces, it's a nucleophilic acyl substitution, the leaving group. You should be able to draw the mechanism out for that, although I would never ask that on a test, the mechanism for the hydrolysis of an amide from thalamide using hydrazine as your nucleophile. But it's really the same mechanism as this one up here, the acid-catalyzed version. The reason why people use hydrazine is because it often is a faster reaction. When you're trying to solve a synthesis problem on a test, a theoretical one, on a paper test, that's not a big deal. But if you're going into the laboratory every day, a faster reaction saves you life. You get more life to live by doing a faster reaction and not sitting around all day waiting for your reaction to get done. So it's useful, and I wanted to mention it, and hydrazine is also a relatively common molecule and may appear on standardized tests, so I wanted to make sure you were exposed to that. You could use H3O+, or hydrazine, it doesn't matter to me. You wouldn't use both, so just one or the other. So to do these Gabriel syntheses, you will always start with phthalamide. you will always rip the alpha hydrogen off using a base like potassium hydroxide. That nitrogen nucleophile will always attack an alkyl halide. And to figure out the alkyl halide, just redraw it and replace the halogen or the leaving group with an amine. Replace the nitrogen in the amine you want to make with the halogen leaving group. And then the third step will always either be hydronium or hydrazine. So this reaction is really, really similar to the malonic ester synthesis, the acetoacetic ester synthesis. Hopefully the principles you learned and the investment you made in learning those reactions simplifies this one. In future videos, we're going to apply this thinking that we went through here to synthesizing some amines using this method, the Gabriel synthesis.